So last time we developed our basic derivative rules, and now we're going to take a chance and look at some examples here. All right, so we're just going to find the derivative. And so the first one, as you're kind of writing that down, y equals 3x to the fourth minus the square root of 2 times x squared minus 3e minus e to the x. So the first thing I want you to kind of remember is, as of right now, we have a very limited scope of what we can take the derivative of with these new shortcut rules. And it's essentially term by term x's to integer powers, and then also we know the derivative of e to the x. So something like number 1, this is what we're equipped to do at this point. So let's go ahead and take our derivative. And so the first one is going to be our power rule. And so let's denote our derivative with a variety of notations. We've done y prime a lot. Let's now take dy dx. So that whole thing is the same thing as saying y prime. So remember, let's break it down real slow on this first one, and then we'll move through them more quickly. Constant multiples get carried along. The power rule says you bring down the positive exponent power there. That's what we've proved it for so far. So bring down the 4 as a multiple times, and then you're going to decrease that power by 1. So it'll be x to the, obviously, third. Again, minus, I can take a derivative term by term. Square root of 2 gets carried along as a constant multiple. 2 gets brought down as that power. And then x to the, we decrease that power by 1, 2 minus 1. This third one is the one that often gets folks in class when we talk about this, because that's not a function of x. That's just a constant. E is like 2.7-ish. So you just have a constant. It's not e to the x. So remember, the derivative of a constant goes to 0. But the last term, derivative of e to the x, that is e to the x. So that's the last one we proved last time. All right, so obviously cleaning this up a little bit, we would never leave it like that. And in reality, you'll jump right to this next result initially. So you'll just say, oh yeah, I bring down the 4, that's going to be 12x to the subtract 1, 12x cubed. Oh yeah, I bring down the 2. Well, I can just write that as 2 square root of 2, x to the first. Constant goes to 0, and the last term minus e to the x. So there's our derivative. All right, number 2, we have f of x equals 9x to the fourth plus 2x squared divided by 5x. So the caution here that I want to make sure that you're aware of, you do not get to take the derivative of the numerator divided by the derivative of the denominator. Okay, do not do this. Okay, so this is the caution. And it's very tempting to do this, but we have not said you can take the derivative of a fraction by taking the derivative of the numerator divided by the derivative of the denominator. And so we need to be really careful about that. Very common mistake when people are first learning their derivative rules. Now, we will get to a point where we are going to have a rule to deal with certain quotients, but right now we're going to have to rely on our algebra. So we're simply going to have to work on first getting this derivative into a form that is what I would call ready for differentiation, meaning I need to just kind of divide, right? As long as you're taking and you're dividing by a monomial, you can just divide each term in your numerator by your denominator and just get this into a form that we can take the derivative term by term. So the first term is our 9/5 x to the third, and my second term here is 2/5 x to the first. And you do really want to think of it like that as opposed to 2x over 5, right? Because the constant multiple is what we get to just carry along when we take our derivative. So it's much easier to work with in that form. So now we can take our derivative. So let's just use the f prime notation here. So we're going to apply our power rule. So the 9/5 gets carried along as a constant multiple. We're going to bring down the 3, and then we're going to decrease that power by 1, so it'll be x squared. Now, the second term, let's think about this. I mean, it does have a power of 1, so if I did bring that down, it would be multiplying by 1, And then if I subtracted, it would be x to the 0. But anything to the 0 power is really 1. So essentially from this point moving forward, I don't want you to have to think about that one so hard. I want you just be able to think that when you have a constant times x, its derivative is just going to be that constant. I sometimes encourage students to think of those terms just like their own little linear function. If I give you y equals 2/5 x, that is a line with a slope that's equal to 2/5. So obviously the rate of change of that term is just 2/5. So you can kind of make some graphical sense of that as well. We went through it with the power rule just to see it does adhere to the power rule, but probably don't want to have to do that every time. All right, and then my first term again, let's clean this up and just make this 27/5 x squared plus 2/5, or if you prefer, you could put it all back together as 27x squared plus 2 all over 5. All right, number 3. Number 3, we have the binomial of 2x minus 3 times the binomial x squared plus 1. And again, we are going to start with a similar caution as last time, which is you cannot take a derivative factor by factor. This isn't just going to be, derivative of, that's 2 times derivative of x, that's 2x, and so that's just going to give me 4x or something like that. So we are not allowed to do that. So don't make that mistake. Again, what can I do in this section? Not a lot. Right now, the only capabilities that I have are to take a derivative term by term, x's to powers. So last time we had to do a little division first. This time we need to multiply it out first. So we're going to have 2x to the third minus 3x squared plus 2x minus 3. And then, of course, once we do that, now we can take our derivative term by term. So now we just have, and hopefully now you're at a point you can kind of cruise through these basic power rules. So 6x squared minus 6x to the first plus derivative of 2x is 2, and the derivative of a constant goes to 0. So there's our derivative. All right. Let's take a peek at a graphical example. So here's a graph right from the Sullivan book, and this time we're going to use the values on the graph to find capital G prime, where capital G is lowercase g minus lowercase f of t. And those are the two functions that are given on the graph. And now we're going to find capital G prime at 0. So the first thing that we want to be aware of on something like this is that because capital G is a difference, we are allowed to take the derivative of a sum or a difference term by term. So that's going to mean that if I'm trying to come up with capital G prime of 0, I get to do lowercase g prime of 0 minus f prime of 0. All right. Probably what you would have done instinctively, but just it's important to recognize why we're allowed to do it. We have a property, a rule that says we can take a derivative of a difference with the difference of the derivatives. Okay, let's take a look at 0 and see if we can figure out what g prime is going to be. Okay, so g is what, the pink function there? And so looking at that pink function, we're going to need to figure out what its slope is at 0. But it's in a portion that is linear. So if I'm looking at this line segment right here, this portion of that line segment, its slope is just simple change in y, as long as I have 2 points on the line, over change in x. So we're going to have 2 over negative 5. So g prime at 0 is negative 2/5. So we're just using the fact that the rate of change on a linear function is constant, and so it's going to be the value of whatever that slope would be. All right, so now we want to do something similar here and we're looking at now on f, and we're trying to figure out f prime at 0. Again, this is a linear segment here. So its slope, again, change in y, so 3 minus the negative 2, over change in x, so negative 5 minus the 5. So 3 plus 2 is going to be 5 over negative 5 minus 5 is negative 10. So it looks like we have negative 1/2. So minus, and then this slope, this derivative at 0 is going to be negative 1/2. And so we're going to end up with, so we have this negative 2/5 plus our 1/2. So what's the negative 4/10 plus 5/10? So 1/10 on that. So it looks like we're going to end up with that equaling 1/10 when we're done. All right, so one more example in this video here. So this is the classic, we've seen this back when we were even using the definitions of the derivative in the first couple of sections, but this is kind of the classic question you're going to be asked a lot is, you know, slope of tangent line, equation of tangent line. You get that question a lot, so get used to it. So f of x equals 4e to the x minus 2x plus pi. Let's start. If we're going to find the equation of the tangent line, we of course need the slope of the tangent line. So if I need to figure out the slope of my tangent line, I of course need my derivative. That's what the derivative gives me. Constant multiple gets carried along. Derivative of e to the x is e to the x. Derivative of minus 2x is just minus 2. And the derivative of pi is of course 0. Derivative constant is 0. So this tells me, and you have various notations for it, that gives me the formula for the slope of my tangent line that I can now evaluate at any x value that we want. So the slope of the tangent line at 0, which of course, if you would prefer, you could have just said f prime of 0. I'm just kind of using different notations, get you used to them. Simply to find the actual slope at 0, we just have to sub 0 into our derivative. Of course, e to the 0 is just equal to 1, so we have 4 minus 2, or 2. Okay, so that is our slope. And to find an equation of a line, we need two things. We need a slope, and then we also need an xy ordered pair. Sometimes they'll give you both, sometimes they won't. If they don't, you need to sub it back into the original. So you would need to say, okay, well, 4e to the 0 minus 2 times 0 plus pi. So if they don't give you the y coordinate, you're always subbing it back into the original. So e to the 0 is 1, so you just have 4 there, and then minus 0 plus pi, so that looks like it's just going to be 4 plus pi as an exact form, and we always want to just default to the exact form. Don't go to decimals unless you're prompted to do so. So we now have the things that we need. We have our xy ordered pair, and we also have the slope. So let's just use good old point slope formula. So to find the equation of the line, y minus the y coordinate is going to equal your slope x minus your x coordinate. So your xy ordered pair that you were subbing in, the x was 0. The y coordinate is the quantity 4 plus pi, so be careful about that and put that into parentheses, and your slope is 2. So as we maybe just kind of finish this out, on the right-hand side, we simply have 2x, and then I might just say, let's just add this entire binomial of 4 plus pi. Let's just add that whole thing over to the right-hand side, you know, rather than like distributing through the negative. You could, and then you just end up adding those two terms separately. So what we would end up with then is simply y equals 2x plus 4 plus pi. And that would be the equation of our tangent line at x equals 0. All right, now a different question. So this one is now asking, where does F have a horizontal tangent line? So notice the first question that we were doing up above said find the equation of the tangent line at x equals 0. This is saying find where F has a horizontal tangent line. So first, let's just kind of rephrase this. So they are saying find where the slope of the tangent line is 0. So a horizontal tangent line is a slope of 0. So they're saying find where the slope of the tangent line is equal to 0. Now, slope of the tangent line, well, what's that? That's just my derivative. So this is just language saying the derivative. So I need to find f prime, but this time rather than subbing in 0, which gives me the slope at 0, which we already know is 2, this time we are setting that derivative equal to 0. So let's go ahead and solve this little exponential equation here. So simply, adding 2 to both sides, we're going to have our 4e to the x is equal to 2. And then just dividing both sides by 4, we're going to have e to the x equals a half. And then the all-important parts, remember to solve an exponential function. That's where, to get into an exponent, you're going to go ahead and take the natural log of both sides here. Natural log of e to the x is just x. That's why we did that. And it's fine. You could certainly leave this as natural log of 1/2. You can also remember that there's a property of logs that says the log of a quotient is the difference of the logs. And so this becomes natural log of 1 minus natural log of 2. And natural log of 1 is 0. And so we end up with this actually just equaling negative natural log of 2. So you could either say, just natural log of a half, or you could say negative natural log of 2. So this is where f has a horizontal tangent line at that x value. And then if they want the y-coordinate as well, remember anytime you have an x-coordinate, in order to get the y-coordinate, it's always going back to the original function. So, you can have your natural log of a half or negative natural log of 2. And then in order to figure out the y-coordinates, you would need to sub that natural log of a half back into the original function. Let me just scroll down. See, 4e to the x, so 4 natural log of a half, and then minus 2x, so minus 2 natural log of a half, and then it was plus pi. And this is one of our properties of logs. It says e to the natural log of a constant like that of something is just going to be that constant. So this is actually just going to be 1/2. And then we have minus 2 times, I think I'm going to think of natural log of a half like we said before, just a little nicer, I think, negative natural log of 2 plus pi. So we have 2, and then this would be plus 2 natural log of 2 plus pi. And if we really wanted to get fancy, we could bring that 2 that's a constant multiple up as a power. And so we could say as a y-coordinates in its exact form, this would be 2 plus natural log of 4 plus pi. And so, it really doesn't get any more simplified than that. I could maybe write the x-coordinate, like we said earlier, as negative natural log of 2. But that y-coordinate, unless we went to decimals, which, if I'm prompted to do, I will, but otherwise I want you to get into the habit of leaving things in an exact form unless you're prompted to go to decimals. So that's what we end up with, kind of a little bit more simplifying than maybe you wanted to do. But this is an important question, part B. You're going to see this type of question, like finding where there's a horizontal tangent line or where the slope of the tangent line is 7 or something like that, where you're setting the derivative equal to a value and solving. So next time we will get into how to take derivatives of products and quotients.